A quick revision of what we have done till now in this series. We defined something called similarity in triangles, and we defined it by saying that if two triangles are similar, two of my triangles maybe if they are similar, if this angle is equal to this angle is equal to this angle, and this angle is equal to this angle. We call this that the corresponding angles are equal. Corresponding angles are equal. And what we did later, that we defined similarity this way. So this happens means the triangles are similar, and we denoted it by this symbol. And as soon as we saw that the angles are the same, the sides were also in a specific ratio because of, so if angles are equal, and I mean when I say angles are equal, I mean the corresponding angles are equal, this implied that the sides are in ratio, or the sides are in proportion. And we had proved this implication. So this implication was not obvious before, and it's not to be taken for granted. We had done quite a lot of hard work in proving this. If angles are equal, then sides are in ratio statement. And we also took some effort to prove the implication other way around, or to prove the converse of the statement, that if sides are in ratio to begin with, if sides of this triangle, or let me draw a new triangle. So say that I know that the ratio of this length by this length is equal to this other length. I'll denote it by red, this red length by this red length, and is equal to the same ratio of this brown length to this brown length. Then we concluded that their angles, corresponding angles, would be equal, and hence the triangles would be similar because we have defined it that way. So these triangles are also similar. So having done all this hard work now, will conclude this video by just stating what are all the axioms of similarity. So we are coming to the title of the series just now, Axioms of Similarity. And as in congruency, we saw that even though all six measurements had to be true for two triangles to be congruent, all the angles have to be same and all the sides have to be same. Here all the angles have to be in equal because the shape has to be maintained, and all the sides have to be in ratio. But it's not always necessary to go through everything. So it's not necessary to explicitly prove all the angles are equal as well as all the sides are in proportion. So these axioms are kind of shortcuts which would lead you to the result anyway, but we just have to check for some subset of those six things we have. So let me name the first axiom, because that's the definition of similarity. We saw that all the three angles have to be equal automatically, then the triangles are similar. Again, this was the definition. I am emphasizing it again and again because similarity may be defined in some other way, then we'll get to this axiom in some different route, but we had defined similarity by definition as the angles being equal. Remember that. So if all the three angles are equal, then my for any two triangles, now I'll name the triangles formally and I'll show you. So if this is one triangle and this is another triangle, and this is say ABC triangle and this is DEF triangle, then I would say that if I don't need to write this down, I think if angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F, then I'd say that these triangles ABC and triangle DEF, where the order is important, remember, because angle B corresponds to angle E, so angle B here corresponds to my angle E in the center, the order is important, is I'll call similar. And is it actually necessary to check all the three angles? Because we know that this is the basic minimum criteria for similarity. Can we reduce it even further? So do we have to check all the three angles if they are equal? What if say I wasn't given this? I wasn't given this. I wasn't given that angle C is equal to angle F. Can I still say this? Because can I conclude it from the information given? Well, the interesting thing about triangles is that angle A plus angle B plus angle C is equal to 180 degrees, right? We also have proved this in one of our videos if you are interested in the proof. But we know that the sum of all the angles in a triangle is 180, and this will hold true also for the second triangle because it's still a triangle, right? So angle D plus angle E plus angle F should be equal to 180 degrees. Well, we know that angle A is equal to angle D, so maybe I'll not call this D, I'll call this A. And we also know that angle A is equal to angle B is equal to angle E, so I'll call this B. And now these two equations look very similar. They are no pun intended there. So I can straight away say that angle C is equal to angle F. The third angle has to be equal. I don't think I need to show you rigorously how you get an idea of it. If even if two angles are equal, say they are 30 and maybe 60 degrees, we know that the other angle will be 180 minus the sum of these two angles, so it will be what, 90 degrees. So it is automatically implied. So maybe I should rub off 1a from my axiom. So my first axiom of similarity is A angle. So if two of the corresponding angles are same, that means A would imply this. So I'll write it this way for now. A would imply that triangle ABC is similar to triangle DEF. So this is one axiom, and I still have a lot of time, so let me go through the other axiom now. We also saw that the sides were in ratio. The sides being in ratio implied that the angles are equal, and hence the triangles are similar. So what if my sides are in ratio? I'll call it S.S.S. And keep in mind that this S.S.S is different from the S.S.S in our congruency, where in congruency we meant S.S.S, the corresponding sides are equal. So corresponding sides equal was for congruency, but here we don't mean this. Here we mean that the sides are in ratio. So as in this case, the corresponding sides are in ratio, and because of the hard work we had done, we say that the corresponding angles are equal, which in turn implies by definition that the triangles are similar. So this implies, again, if you talk about maybe I have the same triangle again. I won't draw it again. Maybe here the angles were not in ratio, or angles were not the same, and the sides were in ratio to begin with. So if AB by ED is the same as AC by DF, this side and this side, they are not equal, they are just in ratio, and is same as BC over EF. So if this happens, if S.S.S happens, that means I can conclude that triangle ABC is similar to, again order matters, triangle DEF. So this is one another axiom, and I don't think we can find out a shortcut there like angle. All the three sides have to be in ratio. You can check it for yourself. Take two sides in ratio and try if you can construct two different triangles, two non-similar triangles, which I'm sure you would be able to. So this is one another axiom. Now finally we go on to another axiom, and we'll see that if we exhaust all the axioms of similarities. In fact, to get to our next axiom, let us quickly see what we looked at in our congruency axioms first here in our rough area, because then we might get an idea what do we have to argue for similarity. So we saw that S.S.S was a congruency axiom. These are congruency axioms. Pardon my writing, but so these are congruency axioms. S.S.S was one. We have an equivalent case here, S.S.S here too. We saw that we had A.A.S or A.S.A or S.A.A. Everything according to us was the same thing. We clubbed it into a single bag because any two angles have to be equal and one side has to be one corresponding side has to be equal. So all these cases in our similarity corresponds to A.A. we studied just now, because any two angles are in any two angles are equal automatically implies the third angle is equal and two triangles are similar. The sides do not have to be equal in this case, so they will be proportional automatically. So this is taken care of. And we saw one another axiom called S.A.S, where these two sides were equal, corresponding sides were equal, and this angle was included in between those two sides. So this was included angle between these two sides. Then we call the triangles congruent. Automatically we'll try to impose this axiom for similarity also. So say that we have two triangles. Let me draw two triangles. Let us see that if this axiom holds first. Another one of my triangle, and I'll call this triangle ABC, ABC, and this triangle DPQ. Okay, and let us try to see that if dp by AB, sorry, dp by AB is equal to dq by AC, that is these two sides are in the same ratio as these two sides, and moreover I know that angle D is equal to angle A. So can we conclude that the triangles are similar? So if S.A.S happens in similarity, where these, I mean now in ratio, these S.S are in ratio, and that's the included, that A is the included angle like before. So does this mean that these two triangles are similar? So like in other videos, we'll have to prove this. We won't take this for granted, so let us prove it. So maybe if I know that angle D is equal to angle A, so maybe I can shift this triangle over here and it will fit perfectly, because the top angle is equal, so the figure has to fit, right? That's just a visual proof for now. You can of course extend this to your rigorous proof later by using compass and cutting the sides here and there, but for now this will do. So this is the common angle, and somehow we'll have to prove that these two triangles are similar. Well, can we, first of all, can we say that this line, I'll call it BC because that's the actual line I took there from, so I'll call this BC, does it divide the side DP and DQ in the same ratio? Because it seems like it does. It seems like BC is parallel to PQ, but does it divide it in the same ratio? Because once it does, we know by our theorems we have studied before, called something called the basic proportionality or its converse, that BC will become parallel to PQ if it does, only if it does, and automatically angle B would be equal to angle P and angle C would be equal to angle Q, and we'll have proved the similarity by angle-angle axiom. So I know this ratio is true, dp by AB. So dp by AB, so AB is now, this point is actually A, so wherever there's AB, I can write it as D because I had moved that same triangle. So this is dp by DB is equal to dq by DC. What if I subtract 1 from both the sides? I have an idea of subtracting 1 because somehow I'll have to get to this length PB, because this is another this length somehow I need as a ratio to show that this line BC divides it into the same ratio. So let's just subtract 1. So what is dB So 1 I can write it as dB by dB because that's still 1, and this I'll write it as dP, and this would be equal to, I'm still simplifying the LHS, so dP minus dB. Now we have common denominator, so we can subtract. dP minus dB by dB will be equal to, this side RHS I am bringing it down directly. You can verify, of course. I in fact encourage you to verify. So this will be dQ minus dC over dC. So have we found something? Well, dP minus dB would give me exactly what I wanted. It will give me BP, right? So BP over dB should be equal to, similarly, CQ over dC. So if I went too fast there, you can always rewind and watch, but I think you'll be able to follow once you watch again if there's some problem. So this is also true. So what did we just show? That if this original ratio given except the -1 part, if this were true, then this is also true. And if this is true, this implies that according to our basic proportionality theorem or its converse or whatever, BC, the line BC, this line, is parallel to PQ. Is parallel to PQ. And what does this imply? Well, this implies, because it's a parallel line and this line PB is acting as a transversal, so this angle will be equal to this angle and this angle will be equal to this angle. The lines are parallel, so the slopes will be the same. So I'll write angle B is equal to angle P. So I could have stopped here because angle B is equal to P, and I also know this. So I also know that angle D is equal to angle A because it's the common angle, right? So I could have stopped here. I have angle, but you do have another, you explicitly you can also obtain this, angle C is equal to angle Q. So whatever suits you. So we have shown that this implies angle axiom holds, and the triangles ABC, what I began with over here, ABC, is similar to the triangle DPQ. Is similar to the triangle DPQ. Hence, all this trouble was for saying S.A.S is also an axiom of similarity where the sides are in ratio, remember. So now I'll write down all the similarity axioms because I think for congruency we studied just this. We also saw that RHS was the same as S.S.S. RHS was nothing different. It was actually a special case for our S.S.S axiom. So I think now we have exhausted everything we had, and these will be the complete set of axioms. So S.A.S, this was the last thing we saw. We also saw S.S.S. Here I mean ratio. The sides are in ratio. Even here I mean ratio. And this angle has to be the included angle. And we also saw angle property. Angle automatically implies angle because it's a triangle. So I think whatever what we have been learning about similarity has been concluded in this video, but all this was only a result of whatever we did in the previous 4 or 5 videos. We derived everything by just defining similarity as angle or angle. We defined it this way and we proved everything else as a result of this. So thank you for now.